right. Welcome, everybody. Thanks for tuning in for another Live Code Tuesday. Today with a special episode. So I have Kai and Florian from ZEISS with me, and today we want to talk about Wasm in enterprise. So a really kind of special live stream as of today. But first of all, welcome to everybody, and thanks for tuning in. And let us know in the comments where you're joining from. So without diving or before diving into the demo and talking maybe about some things that happened last week and the week before, maybe Kai, I can hand over to you for a quick introduction about yourself and why you're here.
Okay, so hi, my name is Kai Walter. I'm with the ZEISS Group. I'm an architect there, and since a few years I'm dealing with cloud topics and enterprise architecture topics there. We have various workloads in the cloud where we process data, and with this data processing, we always look for better ways to do that, saving resources and so on. This is how we came across WebAssembly, and this is why I'm here, or why we are here.
Yeah, we is right. So let's hand over to Florian.
Yeah.
Florian, may you also introduce yourself?
Thank you, Thorsten. My name is Florian Lutz. I'm a cloud solution architect at corporate IT of the ZEISS Group. And I'm basically part of a team that is ramping up new technologies and new projects in the digital space of ZEISS.
Awesome. So as both of you already mentioned, you started diving into WebAssembly and to spot like areas where you can leverage WebAssembly in an enterprise context, right? Before we dive into what you actually do with WebAssembly as of today, let's quickly have a chat about things that happened last week. So last week, all of us have been in Paris for KubeCon EU, and before we dive into like the sessions both of you held, what were the most prominent or valuable moments of KubeCon? Maybe Kai, would you go first?
So for me, it was absolutely the keynote itself. So it was my first keynote I did. I did various talks in the past few years, but I somehow underestimated it. Yeah. So the folks from Fermion and Microsoft, they told me, Kai, come join us at the keynote. And I thought, keynote and so on. And I just realized when entering the stage for the first dry run, really, that's a keynote with 10,000 or whatever people. And that made me humble a bit. But it was a nice experience being out there. And of course, then succeeding that keynote itself, meeting all the people again. So it's my second KubeCon. I've been in Amsterdam last year. Meeting all the folks again was really great.
Yeah, it was like a big get-together for the entire European Kubernetes and cloud native community. That was definitely amazing to see the huge crowd all meeting in the Paris Convention Center. And Florian, what about you? What was your KubeCon moment, so to say?
Yeah, as well. The keynote, of course, was awesome. Even just watching it, knowing the efforts that everybody put in, and then finally seeing it coming together was really great. And I also am going with Kai on the meeting people side. For me, it was the first time meeting most of you guys and most of the Kubernetes community. So I really enjoyed getting to know people you had calls with, from the topics, but never seen in real life.
Yeah, great. So both of you mentioned already the keynote, and I think we will do a quick review of what Kai, Michel, and Ralph from Microsoft, told, or what happened during that keynote. For those of you who were not able to join KubeCon, there is the link again for the keynote, which has been published on YouTube already. But maybe Kai, can you paraphrase the keynote in a quick sentences of what happened? What did you demonstrate to the audience over there?
So Michelle, in the first few minutes, was laying the groundwork, the baseline, again explaining about the various levels of granularity, doing that by referring to a metaphor to boxing, that you have lightweight, middleweight, and heavyweight, and referring to that with to VMs, containers, and now WebAssembly as the new lightweight way of deploying and running stuff. And then I was basically showing what we did in our exploration, Florian and me, together with Fermion and Microsoft, that we basically took or we generalized one of our many data flows we have and run them through WebAssembly on Kubernetes environment. And we showed the figures, the results. I guess we can touch on later also what were coming up. And then after that, Ralph came in and he then talked about that SpinCube, the project underlying our whole efforts, primarily you guys, is turned to open source or requested for open source or submitted for open source, whatever the correct term here is. And with that, basically giving the capability of running WebAssembly workloads side by side with regular classical container workloads very easily with one go, with one tool.
Yeah, this is. I think that's the most or the bold, takeaway from that keynote is that with SpinCube, developers are able to run WebAssembly workloads next to their container workloads. So WebAssembly is actually became last week, WebAssembly became a first-class citizen in Kubernetes. And as you already mentioned, we filed the application. So we, as SpinCube, is an effort from folks at Fermion, at Microsoft, at Liquid Reply, and others. And we filed the application to contribute SpinCube to the Cloud Native Computing Foundation. And so that was an amazing keynote. I mean, the three of you did an amazing job in ensuring everybody's on track. Everybody knows why WebAssembly is so mission critical for the years to come and for building distributed applications, and be walking the audience through a demo and finally hitting the button to submit the application. With that, nice to see that Antoine also joins from Paris. So maybe Antoine, you were also part of the party last week. Please, people, keep on joining and let us know where you tuned in from. Great. So we've briefly chatted about what last week happened. Maybe it's time to dive into what you guys figured out, or how you guys figured out that, or how WebAssembly could be a first-class workload inside of your existing line of business application at ZEISS, right?
Okay. I would touch on that a bit, why we did it and how we did it.
Okay.
So with ZEISS, we have many workloads that basically process messages in the background. Yeah, of course, we have shopping environments with some interactivity, synchronous processing to say, but we have a lot of stuff going on in the background, asynchronous processing, getting orders or whatever messages in, pumping it through our environments. Of course, most of them are Kubernetes based, and as I told in the keynote, whenever we work on a new business model, we have all the freedom we need. We have all the money we need, and the ambitions are high, the stakes are high, commitments are made in business, and then we basically apply Kubernetes to the full extent with whatever capabilities from CNCF projects we need to solve the problem and to fulfill the commitments. After a while, as soon as business settles in, of course, financial aspects are coming more into the focus and basically force us somehow to do a more design to cost design. Yeah, as soon as we understand, okay, this is now what we really need to do or what really has to work, we do a design to cost approach. And additionally, in the beginning also, when you design new systems on the green field, particularly, you can apply all the new practices like event-driven design and so on, and have clear semantic boundaries. But when running in production for a while, we experience, okay, those semantic boundaries for microservices or whatever you call it, they're really nice, but they often do not match the technical shape some environments really need here. So that we are basically forced to have different technical granularity, how we shape service from the semantic granularity, just to account for, I don't know, container image sizes, runtime sizes, scale up, scale down behavior, and so on. So we basically deviate semantically from what we then need to do technically. And this has to do with the large container sizes. If you look at regular containers, we mainly use .NET, but also have TypeScript workloads, whatever you use, or Java, what you have in the enterprise. So we do not do very much Rust, very slim Rust or C++. So our enterprise workloads are from the mainstream languages, if that makes sense. And we were already observing WebAssembly last year on KubeCon. I also did some trials there. But from my point of view, the way to include that on a Kubernetes cluster was given, but it had not yet the right maturity, so to say. And so we started again at the beginning of the year with the Fermion folks and with Microsoft to engage and basically take one of our exemplary workloads we usually use to measure the runtime and throughput behavior and convert it into a SpinCube variant with a focus to see, okay, is the scaling or is the granularity or the size of the container really that small, so that we see a positive impact on the scaling behavior.
Okay. Maybe we can pause at that at this point. So basically, so the key takeaway so far for me is that you have a different, like, let's say, regulatory compliance that every project in your organization has to align with, right? And so you're used to use Kubernetes as an application platform to run your workloads. And you mentioned that you also take or use several projects from the CNCF landscape, so to say. So what are, for example, to give the audience like a sense of what you're using, what are the most prominent projects you use on top of Kubernetes, for example, if you have one or two on your mind?
So in our space, definitely Dapper, because Dapper allows us to abstract away cloud resources from the compute, so that we basically can exchange cloud resources on the borders, and also to allow developers with a different or with their own resources for development experience compared to the production experience. For that we use Dapper. And the other thing, of course, for scaling, we use Kada. Then it depends on the platform. So when we look into multi-tenant platforms, which we already also have, then of course Istio and the like, if we need that kind of network security, network segregation. But usually many of the clusters are really dedicated to the workload, and there we do not care to all the depth of network segregation here. Okay,
so you have Dapper, the distributed application runtime, and Kada for Kubernetes event-driven auto-scaling. All right. So like, I mean, you mentioned service mesh like Istio, right? So it looks like the average like Kubernetes environment, so to say. And now you stumbled upon WebAssembly and thought that it could address some shortcomings that you have with containers when addressing the load, I would assume, right? That line of business applications like yours are facing these days.
Mm-hmm. Yeah. So the topic is here for some of the scenarios, we really need to be prepared for massive spikes of load. And if you look at classic containers, to accept and process the load from the get-go when it hits your environment, we are in the situation that we often need to over-provision. Yeah, we need more. So the things are there really running dry until the load hits in. That means we consume a lot of resources we should not consume, but we need that because scaling is not fast enough to meet the response requirements. So, for instance, getting in a bulk of orders, and then we have a clear deadline. Okay, for 2,000 orders, within 3 minutes for all of 2,000 orders, we need to decide where to produce them, when we can deliver them, etc. And we need to do that response. Yeah. And when we get that batch of orders, we cannot start scaling up at that moment. That would be too late. Yeah, we would not make it.
I see. Yeah, I see.
With WebAssembly, with a smaller packaging size of WebAssembly, we do not need to provision that much because the scaling is much faster. Yeah, so it can pick up the workload faster on the one hand, and if you look at processing of workloads, you can also imagine that there are several waves. Yeah, so we get the order, we do some validation, we do some checking, various waves. And with WebAssembly, we experienced that we can scale down one wave very fast, and by that reusing the same resources again for the next wave. Yeah, with that, basically better being able to reuse the same resources for one processing batch than before. Yeah, because we can move the WebAssembly containers or WebAssembly artifacts, we can move them out of the way faster and bring the others on faster than with regular container nodes. That was our rationale behind it, and that's what we wanted to check out and to test whether our assumptions were correct.
Okay, so being able, so WebAssembly basically is the tag that allows you to scale whenever there's actual need for horizontal scaling without, over provisioning in the first place in order to meet the response time requirements, so to say.
Yeah. And
great.
And then,
maybe a quick shout out to all the folks joining to our stream. So we are here with Live Code Tuesdays. I have Kai and Florian from ZEISS with me. They walk us through their story of how they see Wasm as a great fit for building enterprise architectures. And so people keep on using the chat, please. Let us know what you think. If you have any questions, don't hesitate, just ask. But Florian, you walked us through the why you started looking into WebAssembly and what your expectation was from adopting WebAssembly in a line of business application running on top of Kubernetes, right? So go ahead.
Okay, then I just continue. As I said, we looked into WebAssembly already last year, and you could bring it onto a Kubernetes cluster. Yeah, that was working. But there was a lot of patching and mangling going on. And now with SpinCube, we are in the position where we really can use that side by side. Yeah, so we can keep the regular workload on the cluster and reuse the same node types. We could even in parallel on the same cluster, we can bring up this WebAssembly workloads, which is very good for us, because we do not need to change the operation framework. We can have the same operations and so on. And so for us, it's a low risk move. You can run a WebAssembly with various other orchestrators. Even your company has an own offering for that. But this is not the way we can go in an enterprise. With an enterprise, we can do innovation for running environments really in incremental steps. And so if we do that step, we do not leave behind everything and need to exchange everything. We just can go that step and explore it for certain workloads where we also see the value of WebAssembly.
Mm-hmm. Yeah, you have to keep going, right? The business has to keep on running, while you can only iterate like small pieces of the bigger puzzle, so to say. So yeah, with SpinCube and WebAssembly, so you were basically able to run the WebAssembly workloads natively on the Kubernetes nodes right beside each other. And I think one of the additional values is that you could swap the let's say the architecture of the node. So you could easily swap from, let's say, x64 to ARM64 without having the need to do like multi-arc builds or recompile or cross-compile something, because WebAssembly, is the common layer sitting on top of the metal, so to say.
Yeah, and this is also something we observed and we showed also in the keynote. Yeah, that you can have a workload easily flowing from x86 to ARM in both ways. Yeah, really nice experience. When you do that for several weeks or months, like we did, we do not even realize anymore. Yeah, but seeing it explicitly, it's really nice that you can reuse the same and the cheaper ARM resources. Yeah.
So it's maybe it's worth mentioning that it's not just an innovation driven by, let's say, engineering. So it also you also quickly align with maybe cost efficiency, FinOps targets and whatnot to reduce overall cloud spending, but remain running the same amount of workloads, or even dealing with even higher loads. Right.
Mm-hmm. Yeah, that's right. And here we also have to make a shout out to Dapper, to the Dapper folks, because what we were using in our case is a new sandbox project or sandbox repo called Dapper Shared. Because usually you use Dapper, the distributed application runtime, you use it as a sidecar. Yeah, and what we realized quite fast is okay, when we have a 2 meg WebAssembly container and attach 10 meg or whatever sidecar to it, yeah, then the scaling is it does not make much sense to go the sidecar way. But with a Dapper Shared, we have basically Dapper instances running by the side, and this by the side instances, they fire then on the WebAssembly, on the spin operator, on the WebAssembly deployment. And this allows really this immensely fast scaling on that end.
Yeah, because previously I would assume that the sidecar container is still the piece that, takes some time to actually scale, and by applying Dapper Shared to that. So instead of using the sidecar pattern, you have a shared instance of Dapper running at some in some place, and then the services use it as they would normally use it. So I guess the DX does not change the developer experience. That did not change dramatically for interacting with Dapper, right? It's just a different operations model of Dapper itself inside of the cluster.
And so in the repository where we did all the explorations, for some of the cases we even have both models. So we have the shared model and the sidecar model to also see the difference in the behavior. So we really try to explore every angle of that, and really to get a grip on, okay, where does that really shine? Where does it bring the value? We also saw that if you go into immense scaling, so before Spin Operator, we used the classical Spin Kubernetes deployments. We saw that even some of the plain Kubernetes primitives are standing in the way of the scaling, because they do not scale so fast. The regular deployments like the Spin WebAssembly containers are capable of, and with Spin Operator taking another step, having another scaling mechanism, with that, we really then get the pre-compilation, the caching, and also the fast scale behavior.
Yeah, great. So yeah, Kai was already going into the nitty-gritty details. But let me quickly bring up because you mentioned the repository you guys open sourced. Let me quickly bring in this one, and I will also paste it in the comments. Repository. There we go, so that others can have a look at what you guys actually built in order to verify if WebAssembly is able to address your needs. And I guess with that, should we hand over to Florian in order to walk us through what you guys built?
Yeah, we can do that.
Yep, I would be happy to. I just saw we got one question about the monitoring stack.
Let me quickly bring in this question. So, Moshe, I hope I pronounced that correctly. Can you reuse the current monitoring stack like Prometheus, Cube, State Metrics, etc., used to extensively with containers to monitor the Wasm apps running in the cluster? Yeah, so it's basically what is the observability story that you guys are currently using, and how does that play with WebAssembly?
Okay, so yeah, I take that, Florian, if it's okay. So in our repo, we basically, as we are running on AKS, so we're kind of a bit of a Microsoft shop, like many enterprises. Yeah, so we use we have both cases in our repo. We have Container Insights on AKS, and we also have Grafana Prometheus. So both of them work. And at the current state, we have to highlight that all the telemetry is regular Kubernetes telemetry plus Dapper telemetry, because what is yet missing still, but will be coming in the coming weeks, we do not have telemetry from inside the WebAssembly component. Yeah, so here still some work is going on to make it open telemetry compliant, and when this comes in, then we will have the complete picture. But for the moment, we were basically using the telemetry that the containers themselves and also Dapper emit. Yeah. So again, without Dapper, it would be really hard to get that thing rolling, because that really helped to bridge some of the basic concerns. Yeah.
Yeah, especially in a distributed architecture like as you guys laid out, right? Being able to at least have, from my point of view, right, to at least have distributed tracing is mission critical. And as Yukai already mentioned, we are definitely working on that and hope to contribute or provide those insights as soon as possible. And metrics, I mean, there's like the entire observability story will be addressed at some point. And as you said, Dapper is doing their job already, and we are currently looking into how we can instrument the WebAssembly workloads and provide those telemetry. All right. So Rajat also mentioned in the chat, yes, we can continue to use Prometheus, Cube State Matrix, Matrix dashboards, etc. with SpinCube. Again, we are currently working on providing more insights about what's going on if you're going either all in WebAssembly or having a mix of WebAssembly and containers side by side in Kubernetes. All right, so we were about to hand over to Florian, so let me add his screen to the stage.
Yes,
so
exactly.
With that, Florian, the stage is yours. What have you prepared for us today?
Thank you. Yeah, I would start with broadly describing our workload that we actually run for testing WebAssembly. And we can really focus on the side on the right from the dotted line, because this is actually where the processing of the orders that we're putting in is done. So we start by putting X amount of messages. In most cases, it was 10,000 messages inside a queue, and schedule them at the same time. So at a schedule timestamp to make sure that all of them hit our system at the same time. And then within the first element, we see the distributor. This showcases both the Dapper shared instance that is pulling the messages from the queue, and also the spin app that is processing the messages. For the distributor, this is basically an A/B process. So it checks a JSON value from the message, and depending on whether it is an express or a standard message, it will then push them to the next queue. And then basically,
maybe a quick interruption. Can you zoom in a little bit more? Maybe if you just focus on, yeah, exactly. That makes it easier to read for the folks on the stream. Okay, so we have like that let's say peak load scenario that you guys are testing. So we get messages into an I guess that is an Azure Service Bus queue over there, right? And behind that, there's a distributor who's looking into every message and basically dispatching it again in order to have different processes being started at that point in time, right?
Exactly.
Cool. Okay.
And then, the way goes on for the message. So from their respective queues, it will once again get fetched by a Dapper shared instance and passed to either the receiver express spin app or the receiver standard. And they will once again decide to basically put them into a state store, which is a Azure Blob Storage in our case, as well, once again using the Dapper outbound binding. So all cloud operations are abstracted using Dapper for that.
Okay. Yeah, meaning that basically, although you decided, or as Kai phrased it, you're an Azure shop, right? Dapper gives you the flexibility to, use a different, let's say, state store binding or building block. I think it's building block, right? In Dapper, yeah. Or a different configuration for that building block. So although you implemented it the Azure way, the distributed application runtime, so Dapper, that's the one who's actually taking care of interacting with that cloud vendor specific services or APIs. All right, so we have those 3 spin/wasm squares on the surface. So I guess we dive into one of those a little bit deeper, right?
Yes, we can dive in quickly.
Yeah.
Zoom a bit. So
yeah, while you're configuring your setup, let me quickly do one shout out again to the audience. Thanks again for tuning in here at Live Code Tuesdays. We are looking at how guys use WebAssembly in an enterprise context to address some shortcomings that they have that they figured out with containers. And please join the conversation and let us know if you have any questions. We hope that we can answer them on while Florian walks us through the demo. So Florian, back to
you. Can I just add one aspect? So why did we choose this way of measuring performance? So usually all the performance benchmarks we saw with WebAssembly, someone is really arbitrarily hammering an HTTP endpoint. Yeah. So okay. Yeah. Nice. Yeah. But in our world, that does not say anything. And what we experienced, and this is exactly why we did that, a behavior like a WebAssembly component behaves different when you place it in an ecosystem. Yeah. Because there's an ecosystem or context around it, which influences the behavior of the component, and also the other way around. If this component scales like hell, it has an immediate impact on the ecosystem. And this is why we test it that way, not just hammering HTTP endpoints. Just to add why we choose that approach.
Yeah, that's a valuable addition, obviously. Because as you said, hammering an HTTP endpoint and see how quickly one could respond with HTTP to 100 is nice, but it's does not serve or add big value in an enterprise context. Florian, maybe you can bump the font size to times. Yeah. I think that's easier for people to follow along on the stream.
Yeah,
Thank you.
sure. All right. Yeah, I will just bring you around a bit in our repository. So in the top, you can see the base paths. We basically have a infra folder where we define the infrastructure that we're using. I will go in there quickly to show you how to set up BinCube basically in your cluster. And then the interesting part is in the samples folder. There we have set up different application types or used as well different programming languages to achieve the setup that I've described earlier. And in the end, in the helpers, we can then test this whole setup and fire away the 10,000 messages as often as we want. And we did it quite often. All right. Yep, I will just quickly show you what you need to do to set up the or to use basically the bin operator within your cluster. And with that, I will quickly jump to the main TF. We've used Terraform. It's straightforward for us to use. I think was quite nicely integrated in the ecosystem, so it was nice to use for us. And in here we have the module that is important, which is called Wasm. So this brings up the shim that in the end allows us to run the Wasm on the node, and we pass the Wasm installer image variable in there, which comes from the TFVars file. Basically, this is also from the BinCube organization, directly pulled from the container registry. So you can directly access that one. And I will quickly jump into the
So you basically created all your custom Terraform modules in order to reuse it, maybe across multiple teams, maybe across different environments, right? To easily provision BinCube in any kind of Kubernetes cluster, because I expect, the Terraform provider, I think it just needs a kube context, and then it is able to provision into a Kubernetes cluster.
Exactly. Yeah. And we basically pass the installer image to the init container object, and with that, make sure that the correct shim is there. This enables us to use or to deploy Wasm artifacts in general to the cluster. But what we want to use was the spin operator, and for that we will have to do some more. And in the prepare cluster script, now we have a bit of deviation going away from Terraform, because it was easier and very dynamic for us to test this out. We were doing this before the first release version, so there were quite some breaking changes, and we kept it simple by just using bash script for that. And one thing we have to apply is the runtime class, which I'm showing you in a second, to basically define what is a spin app. And the other thing is basically the spin operator that we're also pulling directly, or the custom resource definition from the spin operator firstly, and in the end as well the spin operator as a Helm deploy. So I can quickly jump to the runtime class just to show you how that looks like. We have defined an agent pool that should run our spin apps, which is Wasm in our case. And in the end, it's just really the plain YAML on that side. So now I would like to show you what we have tested and why we have tested it. I've now navigated to the samples directory, and you can see there are different directories describing the technology stack of the applications that we had a look into. And maybe it's best to do a bit of history session. So where did we start and where did we end up, or maybe even looking into the future, where do we want to end up? So the first, I think the first approaches, Kai, correct me if I'm wrong here, were Rust, right?
Yeah.
Just because it's best integrated into the WebAssembly ecosystem, I would say.
Mhm.
And so basically the Spin Dapper Rust version for us was the first approach. And as soon as we had a Spin application running and we could test it, our approach was to benchmark it against the status quo. So what would we use instead? If we have a look into Rust, what would we use instead? And in our case, this was the Warp framework, which comes as it's usual for Rust with a quite small footprint. And I think the other test that we did was the distroless Rust container. In the end, you have to go that way if you want to have the smallest footprint possible without using the WebAssembly. I don't know, Kai, do you want to talk briefly about your experimentation with distroless Rust? Was it enjoyable?
No, okay. So basically, we had the spin Rust variant running with a certain performance posture, and then we dived into Warp on a regular container, and it was already slower. That was our experience, and I thought, okay, how much energy would I need to put in the Warp variant to get it as fast as this WebAssembly variant? And that's possible. So you can statically compile Rust so that you basically have a container that is just one file. So no operating system, nothing, no distro, nothing, just that one file. And then you have a matched up experience. But still bearing the risk that you might be miss out on stuff or might be missing features. So it's for Rust, it's theoretically possible to match the performance, definitely, because in the end, again, it's just about size, about physics.
Yeah. Oh, maybe before we continue, we have like two questions that I want to bring in. First one is from Ashok. Again, I hope I pronounce your name correctly. Did you face any major issues or roadblocks in terms of interoperability with your data layers and traditional messaging services? And I think this is a quick one. I guess, right?
No, Dapper solved the problem for us.
Exactly, because you have Dapper in place, you were able to quickly use the existing connections and just interact with Dapper via its API.
Yep.
Okay, second one. This is from Moshe again. Very nice. Did you make changes to the AKS nodes, or does Azure provide nodes with the needed runtime to run Wasm? We use EKS, and there is no support as far as I know. Should I take one? Do you? Okay, so as Florian showed in the Terraform, there's Wasm, which will be replaced at some point in the future by Runtime Class Manager. Wasm is basically responsible for installing container D shim for spin on the nodes you decide to, right? So you have to install Wasm, then you annotate the nodes that you wanna make able of running WebAssembly, and then Wasm use a node installer to modify the underlying Kubernetes worker node. This also works with different clusters like EKS, GKE. So the SpinCube documentation on spincube.dev, and I will bring that in over there. We have a list, a living list. We're still trying to find more places where we verify that we can run SpinCube without any errors. So this is currently in need. Microsoft with AKS, they have like versions of containerd shim for Spin already running on Kubernetes, but I think they're a bit dated. That's why we use Wasm also in that scenario on AKS to ensure that we're using latest and greatest. And as Florian demonstrated, you're using a Terraform variable basically to define from the outside which image should be used to modify the underlying node, right?
Yes, exactly.
Cool. With that, let's continue, Florian.
Mhm.
So
Yeah,
maybe quick one question. So warp is like I guess a quite overused term these days again. Can you maybe in a 1 or 2 sentence explain what warp is?
This would be for you, Kai, to pick up.
Yeah. So Warp is just one of the web application or web API frameworks that's available with Rust. Yeah.
Okay.
So you have Tokyo basically as some kind of the HTTP kind-ish framework, and then Warp is on top, a web application framework, very concise, like Express you have in Node.js, and there are many others. I tried 1 or 2. I'm not a Rust expert, and I tried 1 or 2, and I picked the one where I succeeded. Yeah, so I basically was flipping back and forth, and with Warp I was able to succeed and come to a conclusion of what I wanted to test. That's why I chose Warp. So there's no preference on my end.
Okay. Yeah, just to ensure that everybody has the same understanding of when we talk warp, what we actually mean. But basically, it is you created like a let's say Dapperized app using Rust, leveraging the Warp web application framework, compiled that down to whatever architecture is running on your Kubernetes, or your Kubernetes running on top of, and then you were able to compare like pure Rust with Warp performance natively against Rust WebAssembly with Spin performance, right?
Exactly. Yeah.
Okay, got it. Good.
Exactly. Yep. So since we've now covered the history lesson for the Rust variant, maybe we can briefly jump through the TypeScript ones. So basically, TypeScript, what you guys recommended to us, what was closest to our enterprise IT expectations, I would say. So we don't see our developers coding business logic in Rust, at least not if it's not really critical and the performance is really needed there. So we went on with the TypeScript option, and landed, of course, with the name SpinDapper TypeScript, and then benchmarked the Express framework against it. Express, I guess most of the viewers might know, it's just a popular, flexible, and easy to use web server framework in the JavaScript and TypeScript world. And then the last option that we had a look into, and this is, I would say, our North Star, where we want to be in the future, is the SpinDapper.net option. This is also, so we succeeded with replicating the application and getting it set up, but it's really in a prototype state, I would say. There's not much there in that ecosystem right now, but many things are in progress to improve that one as well. And we are also focusing on that variant, looking into the future, because for us, .NET is really something we want to have and we want to stick to, just because it's a skill set within the company that we don't want to lose, right?
Yeah, so I guess that's the bread and butter of your application developers. Is they're used to write the .NET for like decades, right? When make them switch to something. I can imagine TypeScript being the closest thing, because of, I mean, it's made by the same people at Microsoft, right? Or at least the language was crafted by the same folks. Yeah, so .NET, obviously we have some limitations. If I remember correctly, there was like a prototype or an experiment that allowed you to compile a .NET application down to WebAssembly, but that was like or is still like a prototype, and that's why yeah, you went with other languages, let's say it that way, in the first place. Yeah. Okay.
Yeah, but still nice that we were able to get it running, right?
Yeah.
So in the end, we achieved what we wanted, but yeah, performance was not in the expectation window we had. But yeah, okay. That's up to come. So to have a look into an example how this application looks like, I've navigated into the TypeScript the spin option, of course, and we will just have a quick look into the application. I'll guide you through it, what's happening in there, just for maybe all the guys that can't imagine what a spin application does look like. So basically, we're importing different interfaces from the spin SDK. Have a encoder and decoder defined that we're going to use later, and also default headers. And the next step is already to define some routes. We have a health endpoint, then the Dapper metadata endpoint, and then of course for Dapper to duplicate with the options and the post request for endpoints for our application. And in here you can say we have the order ingress, which basically it passes the body to the distributor function. We have the order express in, which passes the body to the receiver function. And for the standard input, it's the same. Also, we're passing to the receiver function. And for all the other routes, of course, we have a not found response.
Maybe one thing. One thing to add here. Although we have 3 services, we only use one code base. Yeah. So this is why everything is mangled into that one file. Yeah, we only have one code base, one source file, but we deploy it 3 times. Yeah? So
I see, with different configuration aspects. Then in that case, okay.
Yeah, I guess only using one code base has 2 benefits for us. One, it's easier to deploy and set up everything for like a new application. And the second thing is it leads to a bit of additional business logic, which is what we want to test here on the performance side, right?
Yeah.
So, I will jump down to the distributor function. The one that initially distributes the messages to 2 different service bus queues. And in here, we basically directly have the whole logic of this thing within the build-up of the URL, because we just, according to the delivery field of the body that is brought into the function, we determine whether it will be put into the express order outbound queue or into the standard order outbound queue.
Yeah, so
And
you're
after
using
that-
basically, you're basically
Yeah.
using just the property of the message payload to construct where it should, the URL where it should head to from the ingress point of view. Yeah.
Exactly, yes.
Okay.
And after that, basically the logic for this function is done. And what we're doing now is to just send out the request with the create operation, basically to Dapper to create a message object in the respective service bus queue.
Mhm.
And it's basically quite similar for the receiver function. We have almost the same line, just that the URL around differs a little bit, because now we're not passing the message to a service bus queue, but we're passing it to a container of a blob storage. So basically we want to store the message, and in the end, yeah, we're building up the operation. So we have a bit of logic here, building up the JSON body and creating the operation with the data that contains the order, and then the metadata that basically gives the blob file its name. Yeah. Exactly.
I see. Yeah. So this is basically what the application developer at ZEISS would do on a regular basis, right? And Dapper takes care of the technical details, where you may not want everybody to go down and learn how to treat the Azure Storage SDK in version 12 for that language and version 17 for the other language. So this is where, let's say, we have the conjunction of two good things, like, right? You have like WebAssembly over here, and you have Dapper taking care about the downstream dependencies. Yeah, that's great.
Exactly. And now we can have a look.
Me quickly bring in the repository URL in the meantime again. So if folks want to have a closer look at what you guys built, then there is that GitHub repository that you should definitely check out. And I will again post that link also in the comments. All right.
Exactly. And now we can have a look how the deployment looks like. So how can we get the application into our cluster? And we have a bit of logic in here because, as Kai mentioned, we tried to design it so we can choose between the option where the Dapper instances are in a sidecar alignment, or whether we want to have Dapper shared instances within our cluster. And we're just setting the pattern here. Then we set some environment variables that we need for deployment, like the service bus namespace and connection string, or the container registry name and endpoints. And important one, of course, the image name, because we always want to deploy the latest image.
Yeah.
This is also what happens in this scary looking block. This is just a bit of YAML query going on, just replacing the image name, or placing the image name basically inside of the workload or the spin definition.
Let me just add here. So why did we use YAML files here? So we could have made up everything, I don't know, with Customize or further Helm or further Terraform or whatever. But at that point, we wanted to have really very simple YAML files, which we can tweak easily and which should also be easier for readers of the repo to follow and to apply in their own configuration. So we did not want to be too opinionated how to deploy. That's the reason why we do this small stunts here. Yeah.
Mm-hmm. Yeah, that's smart. I mean, instead of making like a community member or someone who is looking at your repository learn how to use Customize, learn how to use Helm, that's
Yeah.
straight plain old Kubernetes manifests being altered in a way so that you have that one code base and have like different apps in Kubernetes that maybe in a few seconds that can handle that load, right?
Yes, thank you. And yeah, let's jump down. So this is only relevant for the Dapper shared variant. And what we're doing here is we're deploying the actual instances of Dapper shared. Because if we're not in the sidecar, this is one additional deployment for us. And basically, we're building up the name of the instance here, pulling, of course, the OCI artifact from the container registry, and selecting the node pools. Right here, we have replica count 0. This is because in the beginning, we started with 6 replica count for the Dapper shared instances. Then we took up KEDA scaling to also scale the shared instances. But now, as you will see in a bit, we went back to fixed instances just because the scaling behavior between the Dapper shared instances and the spin apps is so different that we want to isolate the scaling behavior of the spin apps.
I see. So yeah, that you have like individual scaling behavior for the Dapper shared services running. Yeah, makes sense. Okay, cool.
Exactly. And now we can share operator. So we will have a look into the YAML manifest we've already talked about. Here you can see the KEDA definitions, once for the distributor, so for the application. Beneath that, there will be the KEDA definition for the Dapper shared. This will repeat twice because we have, of course, 3 different applications. And then down at the bottom, you can now see the definition of the spin app. So the actual resource type from Kubernetes spin app. Here we got to see the image value that we're replacing on the fly when we do the deployment. We have the deployment annotations used to select our agent pool, and we're passing the Dapper URL as a variable to the app, and that's basically all the magic that's going on here.
Yeah, that's actually illustrating that I mean, it doesn't matter anymore with SpinCube, right? If it is a container or if it is WebAssembly, you can use the primitives like you used to use them for years right now in Kubernetes. So you use, for example, KEDA and point to whatever workload it is instead of a container or a WebAssembly module. Yeah, that's great.
Exactly. And now I can just quickly show you the cluster is cleaned up besides from the telemetry collector. And now I would just quickly deploy the spin Dapper TypeScript option.
Okay.
So we've got a make file for that. This basically calls the build script, which is running here. Which should be pretty fast since we're in the WebAssembly world. And afterwards, it will call the deploy script that we had a look earlier. Maybe we can.
Maybe to ensure. So we are now looking at something. You deploying into an AKS, Azure Kubernetes cluster, right?
Exactly.
Okay. Great.
And one thing to add here, so for the final publish to the OCI registry, we use Spin itself. So Spin itself has a push, and this will push only the WebAssembly module artifact. Yeah, so no OCI container with operating system and any other stuff around. This is only the WebAssembly module. So what we saw in the keynote, this 1.4 max of size.
Yeah, that's right. So just leveraging the raw layers of OCI to get the WebAssembly module into a trusted container registry. And I guess you're using Azure Container Registry, maybe in your case. Yeah, that was kind of obvious. I mean, if you are already in AKS, it makes sense to leverage the container registry there, because then you could go like passwordless and leverage the underlying cloud identities to pull those images as well.
Yeah, exactly.
Yeah, that's great. All right, so we got something deployed already.
Exactly. Now we can see after the deployment finished, we got the 3 spin apps deployed. I can also show you there are the deployments created. Let's first focus on the spin app deployments as well. Those are automatically created with the as soon as the spin apps are deployed. So in the background, it will create for us the deployment and also the service.
It's really fascinating that you work without auto completion. So really Gen X style. Not even I would do that.
Yeah, you need to see what I do because it looks programmed with auto completion, right? So yeah, you can see the services for the spin apps as well. And then also focusing on the shared Dapper instances that we've seen as deployments. You can see for the revisions, the count is set to 1 right now for the applications, and 10 and fixed 10 to the Dapper shared instances. And now we can just jump back to our helpers folder and the order data TypeScript folder, and just start putting some load on there. I will do specific count. Let's take 5,000 messages for the recreation of the messages, and also there's some debug scripts because I've worked on this today.
Okay.
But shouldn't bother us. So basically, right now we set the count of the messages that will be scheduled onto the system to 5,000. With the force flag, we made sure that the 5,000 messages will be newly created, because as we Germans like to be efficient, there's also the option to reuse existing messages to make sure that it's basically the same workload. And the -B option should show us a handy little progress bar as soon as the messages start to get processed.
Okay. So exactly. All the messages are created, and we're just waiting for that scheduled point in time to be hit.
Exactly. Yeah.
Yeah. And also one aspect of keeping the same messages. So we are generating a general structure, posture of messages, and I think it's only a fair comparison if you run the same structure of messages through Express and through Spin TypeScript and so on. That's the reason why we also have that options to keep the message, so that we are sure that we definitely run the same messages through.
Yeah, definitely. All right, so the progress bar is moving quickly. Done.
Yes, and here you can see the evaluation. So basically, the script, it secures a timestamp so it secures the moment the messages are scheduled. So basically, when the first message can hit the system, would be the first timestamp, and then it just checks the modifying date of the last blob that's coming into the storage account, and with that we can calculate the exact time in seconds that the processing or the throughput, if we're jumping back to this image, with that we can calculate the throughput of the application.
Yeah, that's amazing. So we had like 5,000 messages being processed end to end in what was it, 19 seconds, right? Going through all the counterparts of the architecture and having them persisted in the outbox in Azure storage account, was it? Yeah. That's impressive. Yeah.
Exactly. Yeah, and so future runs probably might be a bit faster even because there's caching going on of the application. So the nodes, they cache the artifacts, so they don't even have to connect to the container registry to get the artifact anymore, but really on the scaling out, it can directly load the caching from the file system, the application from the file system with the caching.
Because now for every time you pull an image or an artifact, in the case of WebAssembly, from onto a new node, then it has to go to ACR, do the handshake, grab that OCI artifact, store it locally, extract it, and so on and so forth. So that is obviously speeding up after the first execution of a workload on a particular node. Yeah, I see.
Not only that, it's not only pulling the artifact, it's also converting from WebAssembly in the binary format of the node, because with runtime heavy languages like TypeScript, and I guess we will also see that with .NET and Java, runtime heavy languages, this conversion takes some time, and you notice that time. And with spin operator caching it, this conversion is then cached and it does not need to be applied anymore on that node.
So we can think of like the AOT again,
right,
at that stage, right? Where you know, okay, I pulled it right now. I am on x64, I am on ARM64, whatever, and I, instead of jitting the WebAssembly module, I can compile it ahead for that particular architecture I'm currently running on. Yeah, that makes sense. Awesome. So on top of this sample, because we are already 75 minutes in the stream, I think we should move on and wrap this thing up. So first of all, impressive demo, and thanks Kai for drawing the bigger picture and ensuring that everybody is on track and knows what you guys are looking into and how you think WebAssembly could solve some of the pain points that you have when it comes to scaling, when it comes to be as cost efficient as possible. And you compiled some of your thoughts and findings into an article that you published on dev.to. And I will also ensure that this link finds its way into the comments over on YouTube. So great article if you want to dive deeper into what both Kai and Florian built, and I guess maybe others from your team as well. So then you should definitely follow this article and once again take a look at the repository. So with that, it was amazing to see what you guys actually built and how you tried to do a fair comparison of like spin running in AKS or in any Kubernetes cluster, right? Next to what you were used to use for the past, let's say, decade or so with Dapper and containers. And so it's really, really awesome to see something real being built with WebAssembly and Spin that goes beyond, let's say, sample applications or simple HTTP APIs. So that was really, really interesting. And thanks again to all of the folks streaming in from around the world for joining. And with that, last words from you, Florian and Kai.
Yeah, thanks for having us, of course. It was a pleasure to do the demo. And yeah, excited to look how in future cloud computing will look like.
All
Okay,
right.
same here. Thank you for having us, and stay tuned. Observe this post of mine, because whenever we add technical details or follow-on posts, we will refer it in there or let you know in this post. Okay.
Great. So with that, thank you once again for joining, and see you all next Tuesday. Bye-bye.
Bye.
Bye.
So.